So let's continue with today's lesson. And the concept we are talking about is mass moment of inertia. And in this case, we mentioned IG, the mass moment of inertia about an axis through the mass center G. What if the body rotation not about the center of mass, if another bodies, then how can we find out the mass moment of inertia about the other axis go through the other point other than the center of mass? So let's watch this video.
We've defined moment of inertia of a rigid body already, and we often are interested in it because when we rotate a body about an axis, say an axis that's passing through the center of mass, then our kinetic energy depends on that moment of inertia through that axis. But we may also want to consider rotation about another axis. So suppose we consider an axis passing through close to the end, and we rotate the body around this axis. You can see from overhead, like that. Then we want to now consider how the mass is distributed about an axis that was parallel to the axis passing through the center of mass. So we'll now make a little calculation, but first we want to quote the theorem. So let's.
So that when we talk about the rotation about another point, not the center of mass, we use the theorem called parallel axis theorem based on the video that I just showed you. So let's talk about the parallel axis theorem when we want to find out the mass moment of inertia about the point other than the center of mass. Very important. So if I talking about one body, to make it simple, a circle, a rigid body, the center of mass at point G that you have there, and then any other random point, let's call that a point O, different from point G. And as you can see, if the body rotate about the axis perpendicular to our video, go through G, and that we use IG, mass moment of inertia through G. But if we talking about the moment, the rotation about the axis perpendicular to our screen, our video, go through O, then we have to talk about the mass moment of inertia about the axis perpendicular to the video, go through O. So what is the relationship? So that those two parallel axes go through G and go through O. Let's define that distance between those two is D. So the parallel axis theorem states the mass moment of inertia about the axis go through O equal to the mass moment of inertia about the axis parallel to the axis that we want to find out go through O, but now go through G plus the mass of the rigid body times the distance between those two parallel axes. Keyword parallel, have to be a parallel axis. So md squared. So that is the equation for parallel axis theorem, and we need to have a few notes in here that don't be confused. The IG have to be involved in that equation, not any two random points, and you have that equation. IG have to be there. So let's put down here must be in the equation, not two random points. It can be one random point and the other point IG have to be the center of mass. Be in equation, not two arbitrary points. That is the first note, very important. In there, not two arbitrary points. And then D, what is D? Basically the distance from the arbitrary axis to the parallel axis through G. So it will be the distance from arbitrary axis, go to the axis through G, but it have to parallel to that arbitrary axis, to parallel axis through G, center of mass. Very important. So that is the equation to find out the mass moment inertia go through another axis, go through G. And of course, you already know how to find out the center of mass. Let's give some equation here to determine the location of a composite body that we study in central and distributed lesson in statics. So let's remind or recall what we have it here. Location, locating for a composite body. Composite. So for location about the composites, we can have the equation for centroid to find out the centroid either in 2D or 3D. So we have it now. We talk about in 2D. Then we have it y bar equal to sum of all x for each time the areas divided by the, so it's centroid is center of geometry, and then x bar, and then we have y bar equal to for each point, so location of each point times the areas divided by sum of all the areas of that composite. And then if you have the center of mass, so it will be similar. So center of mass. What we need to do is just replace the areas with the mass. So you have x bar for the mass equal to sum of all the x m hm over the total mass. And then for y bar, we have that sum of all the y times m divided by sum of all the mass. So that is not new to us. And if you recall, if you go to the reference, so as you can see, center of the areas, we make a table. If you recall that, shape, areas, x, moment, x a, y, and then ya times a, y times a. And now for the find out the center of mass, and also to find out the mass moment of inertia, we go to the section 12 in your reference data card. Go to module administration, we have that one. And you see the similar table. We have shape, the mass, x bar times m, y bar times m, and then find out IG. And then we apply the parallel axis theorem. We find out md squared, and then add those two, IG plus md squared. That will be the mass moment of inertia about the point that you want to find out. So that is in the section 12 in your reference data card. Now, what if we want to find out for standard shape? In the area moment of inertia, we also want to find out the centroid of the standard shape. If you recall that, go to the back of the cover, go to your module, and go to the back of the cover. You have inside cover textbook. So with that, I load it in here, and we have everything, unit, etc. The page number 3, that what we study in the centroid. And then go to the last page, center of gravity and mass moment of inertia. So you have different equation for mass moment of inertia. For example, sphere 2/5 mr square depends on cylinder. As you can see very carefully, they have multiple equations, depends on what axis they go through. For example, if the cylinder, you have about the x, we see the vertical in through the center of the section, then it equal to 1/2 of mr square. But if you go through the ix or y, that is the parallel, go to the center G, you see the horizontal axis, then it will be 112 m times 3r square plus r square. So as you can see, different shape have different mass moment of inertia, and it also depends on the axis we are talking about. We have slender rod, the ring, all of that in the last page of the inside cover of the course. So let's get back to here, so you know where to find out the standard shape and to find out the mass moment of inertia of the standard shape about what point, what axis, and then use section 12 to of the reference data card to solve for the problems, to find out the center of mass and also the mass moment of inertia. So with that, let's stop here, and we will have another short video about talking about the radius of gyration.